Hi everyone! As promised, this is our first asynchronous Friday class. It's pretty cool because you can do it whenever you want to on Friday, but the assignments are all due by the end of today, or as it should be Friday. But at least I'm giving you a little flexibility to get it done in the morning, so hopefully you can get an extended weekend. But anyways, I wanted to go over the class objectives for today. These you can find in your Canvas page, and if I were you, I would print these out or have them handy while I'm going over this PowerPoint, because all of these questions will be on your exam next Friday. So make sure you go over these topics, and if there's a few points that you did not get, you can look them up in your reading, and you can also ask me to on Monday's class. The reading assignments are here. They're also listed on your Canvas page, and this link is just that physics crash course that you can watch at your leisure as well. Okay, so let's get started. So the resources for this subject, all of the resources are listed here. Notice these are your reading assignments as well. I read through all of these chapters. It took me a long time to read through them, but I would hope that you will skim through them, look at the pictures, and look for the topics, like I said before, that are found on your course goal sheets. It's pretty cool, but it's definitely, it took a long time for me to read, but I would like you to at least skim through them, read some of the important topics, and get a good grasp on all of the topics that we're going to cover in this PowerPoint. So, pictured here is Maine Yankee Power Plant in Wiscasset. It was formed in 1966. It was a construction that took from 1968 to 1972. It was a 900 megawatt single nuclear reactor. So even though they had a 40-year operating license, the NRC investigated the plant in 1995 due to the reported safety concerns. They found so many safety problems, the company elected to decommission the plant rather than bring it back up to safety standards. Yankee Atomic Power Company is the parent company to Vermont Yankee, Connecticut Yankee, Maine Yankee, and Yankee Row, which was in Massachusetts. Here's another place that you can get information from if you're curious, and this is also where a lot of this information came from in this PowerPoint. This map from August 2019 is slightly outdated. As of October 31st, 2020, there were 94 operating nuclear reactors at 56 nuclear power plants in the United States. The newest operating reactor is Watts Bar Unit 2 in Knoxville, Tennessee. There are only 2 nuclear reactors being constructed currently. That's the Vogtle Units 3 and 4 in Georgia. The chart shows monthly nuclear generation in megawatt hours total for the plants in the U.S. December 2019, we have about 75 million megawatt hours produced by nuclear power. And if you can look closer in this chart, which you can do on your own PowerPoint, the numbers are associated with the number of units per plant. So you can read this: 63% of electricity generation from fossil fuels, coal, natural gas, and petroleum other gases. 20% was from nuclear energy, and 18% was from the renewable energy sources. TWH is total world hours, and basically this just shows how much of the world uses what type of fuel for power generation. And you can see that coal is a big portion of it because it's so cheap. And fun fact, if you don't remember this, the U.S. is like the Saudi Arabia of coal, as it's for oil over there. So that's pretty cool. And nuclear is just this little 10%. In the U.S., we generate the most gigawatt hours or the most hours of nuclear power, but it is not our main source of power generation. I believe we only use about 17% of our generation is nuclear power, as compared to France is 71%. So I think that's on your note sheet as well. So uranium, we discussed uranium the other day. Here's a little picture of the element that you can find on the periodic table. Natural uranium is a mixture of three isotopes, U-234, U-235, and U-238. It's found in nature. It's minimally radioactively dangerous. It is chemically toxic for life as an airborne pollutant, so caution must be taken when mining. From the atomic weight, bingo, most of the uranium is U-238. There's only 0.01% of U-234. There's 0.71% of U-235, the magic stuff that we typically use in a power plant. And 99.28% is U-238, natural uranium. U-234 is such a small amount, it is insignificant. U-235 is fissionable, meaning it can absorb a neutron, become unstable, and split into multiple pieces. U-235 can sustain a nuclear chain reaction. This fission releases a massive amount of heat and is basis for steam generation. U-238 by itself cannot sustain a nuclear chain reaction, which is known as fertile. However, absorption of high-energy neutrons can cause U-238 to fission. Because U-238 by itself can't sustain the chain reaction, we need to have enough 235 to initiate fission and drive the chain reaction. Therefore, we need to enrich the uranium in order to use it as a nuclear fuel. Fun fact, when 1 ton of U-235 fissions, the heat release is equal to the heat release when burning 3 million tons of coal. That's insane. Plutonium is a radioactive element with an atomic number of 94. Remember, 94, atomic number. And an atomic weight of 244. It is the only element with 6 different physical forms. Plutonium has a much lower melting point than uranium, but most can be melted in a vacuum or in an inert atmosphere because it is chemically very reactive to oxygen. All 15 isotopes are radioactive, decaying to stable isotopes of bismuth and lead. The most commonly created isotope is plutonium-239, and it is primarily the product of fast breeder reactors, which are specifically designed to produce more fuel than they use. Fast breeder reactors, you can read more about them in your book. They are basically reactors that make a little extra neutrons so that they make even more chain reactions than like a normal pressure water reactor. Thorium dioxide is used to make up gas lamp mantles because of its extremely high melting point. Because of its abundance, there was a great deal of research conducted using thorium. Absorption of neutrons in a nuclear reactor converts thorium to U-233, a fissile isotope that is not naturally occurring. There are no commercial reactors in the world that currently use thorium as the reactive element for nuclear fuel. Proponents of the thorium fuel claim that there would be less nuclear waste production if thorium were used in a reactor. Supporters say that there is low weaponization potential in thorium, unlike uranium and plutonium. That very detail, that thorium can't be used in nuclear weapons, is the reason research was halted in the U.S. in the 1970s. It's a pretty interesting fact. If the government has no use for it, neither do we, apparently. But I've actually looked online because I was curious about this thorium. There are some pretty cool reactors called lifters that use liquid sodium something or another to use with these thorium reactors, but they're all in theory. There hasn't been enough research behind them. So just know it is one of the radioactive elements that could be used in a reactor, but we just haven't used it. Nuclear fuel cycle. These things, you need to know all about them, and we're going to go over them. Mining and milling. The pie chart shows uranium mining by top countries in the world as of 2012. Kazakhstan, and Canada are the top producers and have been for at least the last decade, followed by Australia and Namibia. Mining is done in two ways, underground and via an open pit. The picture of Mi Vida uranium mine in Moab, Utah. The alternating red and white green sandstone is where the uranium deposit can be found. Right there. This type of deposit is easier and cheaper to mine than other types because the uranium is found close to the Earth's crust. Nice. Open pit mining, also known as strip mining, removes surface soils and rocks to get the uranium ore below. Uranium ore grades are usually less than 0.5%. Once the ore is exposed, a series of benches or steps are cut into the earth to make ore removal easier. Benefits include better ventilation, less expensive than underground mining. Downfalls are it's a huge footprint, waste piles, and remediation is extremely costly. Nearby communities can be negatively impacted due to dust, noise, and groundwater contamination. So no one likes to be neighbors with this thing. But who wants to work in a little mine where you get radioactive black lung, right? Okay, moving on. Underground uranium mining. Underground mining is used to reach higher concentrations of uranium that are too deep for open pit mining, usually greater than 350 feet. Uranium ore is dissolved by pumping solution underground, bringing it back up, and extracting the uranium from the solution. Benefits are a smaller footprint, less rock waste, and through advances in technology, less risk to mining workers. It's extremely expensive and there is potential for serious impacting local aquifers. Kind of like natural gas, you know. If we crack one of these layers and we get into the aquifer, we're going to screw up a lot of people's well water. Milling is the process where uranium is extracted when concentrated from the ore that has been mined. Ore is crushed and leached with acid and recovered using an ion exchange process. Excess water is filtered and roasted off. This milling process yields the yellow cake, which is U308. It takes a ton of ore to mine 5 pounds of uranium. Only 0.25% of what is mined is uranium. What you need to know here is that yellow cake is converted to uranium hexafluoride through a multi-step chemical process. Uranium hexafluoride is a gas, also known in the industry as hex. At this point in the process, the uranium hexafluoride is at about 0.71% concentration of U-235. It is concentrated so that there is just the right amount of U-235 compared to U-238. Through the enrichment process, the uranium concentration is gradually increased into a cascading method, either by gaseous diffusions or through a centrifuge. The centrifuge also cascades in nature and is done repeatedly until the appropriate concentration is reached. Only 2% of the energy is needed to enrich uranium during the centrifuge process compared to the diffusion process. So pelletizing. The uranium oxide powder is then blended and sieved to make a homogeneous lot. Powder is fed into dies and pressed into cylindrical pellets. Pellets are heated in a furnace at 3100 degrees Fahrenheit for 4.5 hours, ground and inspected. A boron coating is added to the outside to help control the reactivity. And you'll hear that boron chemical quite a bit in nuclear power because it is one of those things that slows down the chain reaction. It's also used as a moderator. As a side note, this is how downblending occurs. Downblending is the process of taking highly enriched uranium used in nuclear weapons and reduces the concentration of U-235 to lower levels so that the fuel can be used in power plants. In 1995, the Megatons to Megawatts program started downblending U.S. and Russian weapons grade uranium into LEU, lower enriched uranium. From 1995 to 2013, the equivalent of 20,000 nuclear warheads were downblended to LEU. So I figure that's a way that we can make the world a happier place because there's less nuclear bombs that are going to kill us. So that's comforting. Encapsulation, aka cladding. These tubes are made using zirconium through a cold tube drawing process, similar to what we saw in the video last semester on making tubing. Each pass needed heat treatment, and there were several passes. Heat treatment occurs under a vacuum. Then the rods are cut to length. These are inspected several times. Samples are taken to verify the material composition. Rods are put together so that the fuel pellets containing the proper amount of U-235 per rod, these are weighted and recorded. The stack of pellets is inserted into the fuel cap, is welded to the cladding, and the upper level plenum spring is installed into the cladding. The tube is then inserted into the weld chamber where it is evacuated, vacuumed out, and pressurized with helium. At the top end, the plug is welded. The rod is then checked for helium leaks. So this is the assembly. The cladding's the outside part, and there's a little spring in there. Your fuel pellets are here. A little spacer for good measure, and there's a plug down here and a plug up here. Assembly. Rods are then put together in these bundles. These steps are done in the horizontal position. There are upper and lower spacer grids that keep the rods in their correct position. Grids are made up of strips. Each strip is numbered and traceable. The grid is laser welded at each strip intersection, meaning there are 500 welds per grid. All dimensions and welds are carefully checked. Grids are installed to fixtures to keep them steady. The guide tubes are inserted and secured by welding them in place. Think of these like the stay tubes in a fire tube boiler. They provide rigidity and stability to the overall fuel assembly. Fuel rods can then be inserted. They are scanned so that the correct rod is located to the correct spot in the grid. All is carefully calculated and documented. Then the assembly is put in the vertical position for inspections. Bundles are shipped horizontally in licensed containers. There are usually 1 or 2 bundles per shipping container. The CANDO reactor design operates a continuous refueling mode, so there is no shutdown required. Most PWR, pressure water reactors, were originally designed for annual refueling, where 1/3 of the fuel was replaced each outage. Through operational experience and data, the trend has been pushed to 18 to 24 months of runtime between refueling. Fuel costs are higher when the shutdown occurs after more time has passed, but the longer the cycle, it is more cost effective due to the overall reduced number of outages over the life of the plant. There are also fewer licensing submittals that need to be done, as well as lower replacement power costs. So, less paperwork, less money, better to not have to do this so often. Burnup is a way to measure how much uranium is burned. In other words, how much uranium has split inside the reactor, measured in a gigawatt days per metric ton of uranium. 2 decades ago, average burnup was 35 gigawatt days per metric ton of uranium. Now, it is over 45 gigawatt days per metric tons of uranium. This increased burnup capability means batch size reductions as well as longer cycles. Today's units are loaded with batch sizes once used for annual cycles and utilize a checkerboard scheme to replace the fuel bundles. mPower SMR reactors replaced the entire load of fuels after 4 years of continuous operation. As nuclear fuel is used, characteristics change. There are 4 things that happen. They are all independent on the level of burnup of the fuel. 1. Dimensional structural changes of the fuel. There is growth, rod diameter can enlarge, fuel density changes. 2. The cladding, water cell corrosion, and hydriting. Early on during burnup, the cladding reacts with the water and there is a thin adherent oxide layer on the outside of the cladding. The oxide layer is impacted by the time the fuel is spent in the reactor. The neutron flows, water chemistry, and coolant temperatures. All must be monitored. Fission gas release. If there is a fission gas release, this can cause high internal fuel rod pressure. Pellet cladding interaction, PCI. This is when there is a contact between the individual fuel pellets and the cladding. It happens when there is a rapid change in power level. The PCI occurrences had led the power maneuvering guideline development. It's also the reason helium is added inside the cladding to help prevent this contact. Once the fuel is used, there are 2 options. 1. Recovery of the spent fuel. Fuels can be reprocessed and used again to make power. This is the closed fuel cycle. Option 2. Disposal. This is the open fuel cycle. Either way, the disposal of high-level waste requires safe, undisturbed confinement for hundreds of years. The goal of an integrated nuclear waste management program is to immobilize and isolate the nuclear material from the ecosystem until it's no longer a significant threat to the environment. Since the 1970s, waste storage regulations have progressively been more rigorous. Every nuclear site that were designed with the idea that there would only be closed fuel cycles, therefore they had only certain size spent fuel pools and did not plan to have long-term fuel storage on site. In the 1970s, recycling spent nuclear fuel was banned in the U.S. The law was rescinded in the 1980s, but the damage had been done. Plants built later included designs with larger spent fuel pools. The nuclear industry has met this challenge by working to produce less waste, have longer fuel cycles. Nuclear plants have re-racked fuel in spent fuel pools and utilized neutron-absorbing materials to lower reactions and therefore hold more fuel spent rods. Even with these changes, spent fuel pools can't hold all the fuel needed for the life of the nuclear plant. The level of radiation determines the handling and storage steps that are necessary. Above all else, we must protect the groundwater against contamination. You may want to write this stuff down. Byproducts of spent fuel are liquids until they go through the vitrification process. This turns them into a solid. It's highly radioactive. Federal facilities have been reprocessing spent nuclear material since the 1940s. Nuclear submarines. Transuranic or waste incidental to reprocessing. Atoms of man-made elements containing isotopes with atomic weights greater than U-238 has a half-life greater than 20 years. This exceeds 100 nanocuries of radiation per gram. It generates little heat. If it's this type of waste, the storage requirements are a 55-gallon drum in liquid form on site. Relatively low radioactive emissions, secure locations but not isolated locations. Mill tailings. Here are the storage requirements for that. I'm not going to read it to you because you can look back at this. Low-level waste. There are 4 subcategories of low-level waste. A, B, C, and Below Regulator Concern, or BRC. BRC is so low that it is simply disposed of regularly. Years ago, when the first commercial sites began accepting low-level waste in 1963, they would bury this waste only 15 feet deep. it wasn't successful. There were leaks and many problems. In the 1980s, the Low-Level Radioactive Waste Policy Act was passed, which placed responsibility of LLW disposal on generator states and recommended regional facilities. Nowadays, the storage containers are much better. There are also vaults either above or below ground. Part of regulations of 1987 were that the EPA and the NRC established that repository standards must include: 1. Any stored spent fuel, or HLW, must be recoverable for 50 years after closure. Wow, 50 years. Waste packages must be leak-proof for a minimum of 300 to 1,000 years. And 3. Only phased release of nuclides would be permitted for a subsequent 9,000 years. A number of options were considered for a long-term HLW storage: geological repositories, under the sea, under Arctic ice, and launching into space. The only geological repository option made financial and practical sense. The geological repository was suggested and tested at the Climax mine in Nevada, using vertical boreholes in conditions where studied for years, and it determined that this was a safe option. The greatest challenge is finding a suitable location, away from national parks and away from large populations. We also need to find the right geological media. It has to have rock, salt, granite, clay, because those are hard, impervious types of media. We must also consider the value of materials left behind that can't be mined ever. After serious debate, Yucca Mountain was approved. Tunneling began in 1994 to properly assess the mountain as a geological repository. Secretary of Energy recommended Yucca Mountain to President George W. Bush. The President agreed and notified Congress. Both Senate and the House approved, and it was signed into law. Then the Nevada Governor Kenny Guinn vetoed the decision, so the bill was returned to Congress. They overrode the veto, and then the plan moved forward. 2003, the project was over budget and behind schedule. 2004, target 2010 opening was in question. 2008, the reassessment of the milestones happened. In 2009, budget reductions. 2011, President Obama announced an end to government funding of Yucca Mountain Geological Repository. Remember, all spending goes through Congress. The NRC suspended the project and its licensing. Wow, what a waste of money. 2012, Obama established the Blue Ribbon Commission on America's Nuclear Future to recommend policies and procedures and recommend new strategies. Some of the recommendations were new facilities, siting processes, and authorization of consolidated interim storage facilities, and establishment of a new waste organization. In 2019, President Trump's administration has made a play to reclassify waste from nuclear weapons, prompting backlash from all the states that contain these federal sites. At one point, Trump supported the refunding of the Yucca Mountain Repository, but then decided against it after an intense protest from Nevada. The search for a solution continues. Wow, what a sequence of events. The picture on the right is from Maine Yankee, Wiscasset. This is their Independent Spent Fuel Storage Installation, or ISFSI. There are about 542 metric tons of spent nuclear fuel stored at Maine Yankee. According to them, it costs roughly $10 million per year to maintain the 64 canisters of radioactive waste. Millions of dollars of damages are being paid to facilities for costs associated with keeping spent nuclear fuel on site. Every few years, Yankee Atomic Company uses the DOE for damages. ISFSI ISFSI sites must be protected 24 hours per day by heavily armed guards, and they must keep up with inspections. This figure from Steam 42 shows how a dry storage cask is put together. The spent fuel bundles are loaded into a canister, thin-walled steel canister. This canister is dried and filled with an inert gas and sealed welded shut. The canister is transported to the storage overpack module, which is the thick concrete case. The casks provide shielding from radiation and have ventilation built in for cooling. New nuclear plants are designed for 80-year lifespans because there is no long-term spent fuel storage solution. They need to be prepared to store the fuel in ISFSI and must be designed to hold the fuel for a lifetime of the plant. Fun story here, I actually have an old boss that works here, and all he does, because he used to work at a nuclear plant down in Florida, now all he does is hangs out there and gets paid to sample the water every day to make sure it's still radioactive and how much it's decaying. And he makes a stupid amount of money to do that, and he's home every night. So just another thing you could get into. So here's a video. I'm not going to play it for you on this, but I'd like for you to watch it. It's pretty interesting, and I might have you do a discussion about it in the assignments for this week. So I hope you guys enjoyed this PowerPoint, and I'll see you guys next week.